Welcome back, everyone, to our third lecture in the day. Gary, please.
Thanks. So welcome back to part 2 of the second part mini course. So today we're going to finish off the enumeration part where we enumerate candidates, whatever that means, and hopefully we'll see what that means in not too many minutes later. So I just want to quickly remind you of a couple of things we've been looking at. So first, an n-Seidel, as I write, just means an n by n Seidel matrix, and this just looks like this. So it's a symmetric matrix with zeros on the diagonal, plus and minus 1 on the off diagonal. And we also had a couple more definitions that we'll need to remember. So first of all, I'll redefine type 2 polynomials. So we call polynomial p of x type 2 if its ith coefficient is divisible by 2 to the I. So formally, if we say the coefficients are a sub I, then it's type 2 if 2 to the I divides a sub I for all I. And a slightly weaker condition, which we call weakly type 2, 2 to the I minus 1 divides a sub I for all I. So that's a definition we introduced. And the reason we introduced that is because we find that the characteristic polynomials of Seidel matrices are almost directly type 2, but not quite. So this is a lemma that we built up to last time. I just remind you of this lemma. This says that if S is an n Seidel matrix of order n, and k is some odd integer, then the characteristic polynomial of S minus ki is weakly type 2, and if n is even, then this will be type 2. So if n is even, this characteristic polynomial of S minus k times I, S minus k times I, type 2. Okay, so this is what we built up to last time, and today, well, I'm going to start off by showing you a very important technical lemma that uses these facts. All right, so let me try to first state this lemma that I claim is very important. I'll try to convince you why this lemma is very important / useful. So we have a few assumptions here. So first we suppose that D is some natural number and S is an n Seidel matrix, so a Seidel matrix of order. And lambda 0 is the smallest eigenvalue, and we're assuming it's an integer. So hopefully you can see this is a reasonable assumption, and we assume the multiplicity of the smallest eigenvalue with multiplicity at least n minus d strictly greater than 1. So again, hopefully you can see this is quite a reasonable assumption, because if the smallest eigenvalue has multiplicity 1, then it's not going to be a very good equiangular line system, according to me, because I want to have a lot of lines in a small number of dimensions. Next, k is an odd integer, and now we define something slightly technical. Here's theta. Okay, so theta is the first kind of slightly awkward thing to define, and this is going to be the minimum of the following set. So the minimum of eta, natural number, such that eta times 4 to the eta minus gamma of n over eta is strictly greater than something. So this complicated looking expression, I haven't told you what gamma is yet, so I'll tell you that in a minute.
The sign is the big one, right? The greater sign is supposed to be.
Oh, it should be lower, yeah. Sorry. My wonky writing there. Yeah, please interrupt me if anything looks strange. Very helpful. So this thing is greater than, strictly greater than, n times n minus 1, and this is something you might recognize from the relative band, or the proof of the relative band. Lambda 0 squared n minus d plus 2k lambda 0 n minus d plus d times k squared. Luckily, I finished that. So this is a strange looking number, but hopefully it will make sense. And I'm sorry I put it on a bit of a slant. What is gamma? So I'll try to keep this all on one blackboard. I'll put gamma up here. Gamma is just an indicator of if n is even or not. So we put a 1 if n is odd, 0 if n is even. Gamma of n is just telling you whether or not n is even or odd. Okay, so that's all of the assumptions. What's the conclusion? So the conclusion is, it's readable if I write it here. Let me draw a line underneath this set. So here comes the conclusion. If theta is at most d, then it tells us more factors of the characteristic polynomial of S. So we can write the characteristic polynomial of S is equal to x minus lambda 0 to the n minus d times x minus k d plus 1 minus theta, and then some other factor. Is this legible? Anyone can't see this? So this is, I mean, you can see this is quite a technical looking lemma, but I claim that it's very important, and hopefully you'll be able to see why. So I want to start by proving this lemma. I won't give the full proof. I'll just do the case when n is even. Okay, so we know that lambda 0 has to be odd. That's because its multiplicity is bigger than 1. So we know from yesterday, if you have a Seidel matrix and it has an even eigenvalue, then that has to have multiplicity 1. So since we know the multiplicity is bigger than 1, we know that the smallest eigenvalue is odd. And next, we're going to denote by lambda 1 up to lambda d. These are the other eigenvalues, other d eigenvalues of S. Okay, now we're going to use these properties of Seidel matrices that we've seen before. So the trace of a Seidel matrix is 0, just have 0 on the diagonal. The trace of a Seidel matrix squared is n times n minus 1. And if you put these two things together, you can obtain the following. So let me just go a bit slow. I'm not going to jump since you might not remember from the first lecture. So if we sum up these other d eigenvalues, and since the trace is 0, we just get the negative of the contribution from the smallest eigenvalue. And similarly, we can do something for the sum of the squares. Lambda I squared equals n times n minus 1 minus lambda 0 squared n minus d. So these are straightforward consequences of these traces. And if we put them together, we get the sum I goes from 1 to d lambda sub I minus k squared is equal to this thing here. So you see we get an n times n minus 1 coming out, and some stuff involving k. So if you work it out, you get this quantity here. And I just want to highlight this. I'm going to attempt to use a different color, so I'll just put a circle around this and call this R. So I use capital R for this quantity here, so I don't have to rewrite it out. I can just say that this is equal to. Okay, so that's where this quantity is coming from. Okay, let me try to move this up a bit. So now the characteristic polynomial of S minus K times I. So let's consider this characteristic polynomial. We can write that if we like as just characteristic polynomial of S, where we shift. And we know what this is because we've written down all the eigenvalues. Here we get x minus lambda 0 plus k to the n minus d, multiplied by the product. I goes from 1 to d, x minus lambda sub I plus k. So this is just the characteristic polynomial of S, which has eigenvalues lambda 0 and lambda 1 up to d, and we're just adding k to everything. So this, nothing surprising here.
Sorry, I know you're a couple steps ahead, but I'm just, I feel like I'm missing something, like
Okay.
the sums of the two sums of the lambda I and lambda I squared, I feel like I've missed something. So like, why isn't it the sum of lambda I from 1 to d is just minus lambda naught?
Because it has multiplicity n minus d.
Yeah, okay. And then why is there, okay, nope, no, I got it. Thank you.
Yeah, same reason. But thanks for the question. So we have this expression, and the first thing we can do is remember the lemma from last time. So from last time, we know that if k is odd, then this characteristic polynomial should be weakly type 2 and type 2 if n is even. For this proof, I'm assuming n is even. So therefore, the lemma tells us this is type 2. And now we're going to use the factorization property for type 2 polynomials. So because k is odd and lambda 0 is odd, this factor is also type 2. Is also type 2. This is type 2, and these factors are type 2. And so therefore, by the factorization property we saw yesterday, this has to also be type 2. Okay, so this implies that this product from I equals 1 up to d x minus lambda sub I plus k, this is also type 2. So how do we use this? Well, if it's type 2, then 2 to the I divides the ith coefficient. So if we look at the constant coefficient, that has to be divisible by 2 to the d, because this will have a dth coefficient. So therefore, this product I equals 1 up to d lambda sub I minus k. This is just the constant coefficient of this type 2 polynomial, and so therefore 2 to the d should divide this, since it's type 2. So we can write this as 2 to the d times q for some integer q. This is where we're bringing together lots of properties of 2's and characteristic polynomials of Seidel matrices. Okay, so next we're going to apply a very common trick, the arithmetic geometric mean inequality. So the inequality of arithmetic and geometric means tells us the following. So first of all, that d to the d times 4 to the d is strictly greater than r to the d. And this is where my board placement hasn't quite worked out. I think maybe, did I forget to assume this at the beginning? Okay, so this is something I need to assume here. So here theta is at most d, and so here I'm using d times 4. D times 4, and this will just be d minus 0 divided by d, so that'll be a 1. So maybe I should just write that over here. So we assume times 4 strictly bigger than r. This is using this assumption. So I'm starting off at the worst case where I just have theta equals d, and then we're going to see how we can kind of take more steps. So this is part of the assumption of the lemma in the n even case, because this eta is a d, then we'd have 4 to the d minus gamma n is 0 because n is even, so we have d divided by d is 1. And so this assumption just turns into d times 4, and this yellow thing is r. So this is assumption of the lemma. And so if we take the d power of this, we get this inequality. And r to the d, well, we know that r is equal to this one here. So we can write that down. So r to the d is equal to this sum, I goes from 1 to d lambda sub I minus k squared to the power d, taking just the d power of the stuff. And now we finally use the Amgm inequality. So this will be d to the d times the geometric mean, taking the d power of everything just so I don't have to take the dth roots when I look at the geometric mean. So I'm not sure if this is so familiar to everyone, but I just felt it's easier to write like this. So this is where the Amgm is coming in. And so now we have something in terms of this product. So I'm linking together this sum of squares and this product of squares. And over here, we already learned something about this product. This product is the same as this product here, except we're just squaring everything. So we know that this is equal to d to the d, and then we just need to square this thing, multiplied by, so instead of 2 to the d, we have 4 to the d, and instead of q, we have q squared. And now if we look at the right, we have d to the d times 4 to the d times q squared should be strictly less than d to the d times 4 to the d. So the only way this can happen, since q is an integer, this tells us that q has to be equal to 0. And what does it mean if q is equal to 0? Well, it means that this product is equal to 0, and so therefore k must be equal to one of the lambda i's. Therefore, there exists some I such that lambda I equals k. And so this is how we can find that k has to be an eigenvalue. Okay, and then the proof, you just keep repeating this until this assumption no longer holds. So the reason the Amgm gave us that k is an eigenvalue is because of this inequality. So we just keep going until this equality no longer holds. Is that a question?
So if q is positive, then that inequality fails, right? But if q is 0, this still fails, right?
No, because this is positive.
That's positive. Okay,
Yeah.
sorry.
So anything positive is bigger than 0.
I'm sorry, it's my stupidity. Okay.
So the only way this inequality works is it forces q to be 0. Okay, and just to give you an idea how to repeat the argument, since the first step doesn't look very general, the general step looks a bit more like the following. So after we've established that one of the lambda i's is k, we can just repeat the idea. So this time, if we write out what does our characteristic polynomial of s minus k I look like, again, it's just shifting the characteristic polynomial of s just by adding k to everything. And so this time we have a k eigenvalue, and so that will give us an x factor. So we'll have some x factor, then we'll get the factor coming from lambda 0, and then finally this product at the end, which is just the same, x minus lambda sub I plus k. We just try to remedy this. Goes from 1, this time d minus 1, right? Because one of our d eigenvalues we just found out is equal to k, so that would be a x factor. Okay, and then you just repeat the argument. So you just keep repeating until it doesn't hold. And that's where this strange definition comes in of the eta. Okay, so that's just telling you how far can you push the argument. That's what theta is telling you. Okay, so that's pretty much the proof of that. Hopefully you can see that the 1 here is coming from weakly type 2. So we just lose a factor of 2, and that's where this 1 comes in, which makes it look very ugly. One way to get around it would be just prove 1 lemma for n even, 1 lemma for n odd, but matter of taste. Okay, so once we've established this lemma, how do we proceed? Well, now I want to convince you that this lemma is very important, and it will take a bit of time for that to sink in. So first of all, let's see how this lemma helps us with dimension 14. Let's just quickly do an example of applying this lemma. Example. Oh, the camera's not following me? Camera, please follow this way. Is it going to follow me? It no longer believes I'm a human.
Wiggle your remote.
I don't have a remote.
I mean, it's the sensors inside your microphone.
Are you sure?
No, is that not what's going on?
It's not moving.
Okay. So for those people in the room, you can give us an example.
Yeah, but just in case there's someone online who might be interested. Okay, oh no, it's following the wrong person. Okay, let me try to get it back. Follow me, please. This way. Come on. Come on. All right. So example, d equals 14, what happens? So we just essentially apply the statement. So luckily the lemma is there for us to compare. So suppose there exists an n-sidal matrix where n is equal to 29 with smallest eigenvalue equal to -5. So this is what you would need if you do have 29 equiangular lines in dimension 14. Okay. The next thing to do is think about what should k be. So in the statement of the lemma, k is just some odd integer. But what you really want to choose if you want this thing to work is you want to find something that minimizes this right-hand side. Because if you want this to give you a decent value for theta, which it usually doesn't, by the way, you want your k to make this right-hand side as small as possible. You typically want to choose, quick comment, so k will be the closest odd integer to, I think it's -λ0 n minus d. So that's what you should go for. How do you find this value? Well, you just minimize the right-hand side. Okay, just do a bit of calculus, get this one. And then you take the closest odd integer to that, so you're kind of minimizing it with respect to being an odd integer. So in this case, we'll get k equals 5. And now we can work out what r is. So r in this case would be 37. Next step would be figure out, so theta, you just need to check some values. And so I'll just try to convince you that theta is 11 in this case. And so you can check that by doing 11 times 4 to the 10 over 11. If you work that out, you'll get 38 point something, which is strictly larger than 37. And if you tried a smaller value of theta, so for example 10, then that would be 4 to the 9 over 10, which will give you something like 34 point something, which of course is less than 37. So we worked out everything in the assumption, and so now we can apply the lemma. We see that theta is less than d. Here d is 14, theta is 11. So if we apply the lemma, oh, I can actually lift this up. So by this lemma, we can write the characteristic polynomial of this sidal matrix has the following form. So x plus 5 to the 15, x minus k, which is 5, and then d minus 1 minus theta gives us 4 in this case. And then we still get this remaining factor. So this lemma helps us work out a few more eigenvalues kind of for free before we do any messy computation. I guess saying messy computation might be a pleonasm, but I don't know. In my case, I think it is. So just to keep a record of this, the degree of this unknown factor at the moment is 10. Okay, so that's just an example of how you can apply this lemma. So in this course, I want us to see how to deal with d is 14, 16, and 17. And so I'll just do a brief summary of those values. So I'll just summarize that in a table. So here's n. And here's characteristic polynomial of S. So D14, 29, 16, 41, 17, 49. So these are the n that we want to kill in order to establish the constructions that we know of are the best possible. My chalk is dwindling. So backup chalk number 1. As we saw for D equals 14, we get this one. For 16, we'll get
Right.
Oh. Yeah, I'll use someone.
okay. For D16, we get this one.
Thank you.
And for 17, we get this one. 32 x minus 9. And these factors. So after we've applied this lemma, the next thing we need to do is figure out possibilities for these factors. Okay, and now I'll just highlight the degree of these things, the degree of these phi. We saw this is 10, this is 13, this is 13. Our next job is to enumerate this, and this is where we have to roll up our sleeves and turn on our computers, although maybe we would have turned on our computer to compute theta already. So that's the next thing we're going to do. In fact, I might write this over here since it's quite relevant. Is the camera still following me? We'll think about properties for each of these phi. Camera?
Oh, that's good.
Thank you. It looks like this. So it goes from I is 1 up to its degree. And we'll give it coefficients bi, degree phi minus I. And let's just note, what do we know about these factors? So first thing we know, first thing we know is that B0 is 1, it's monic. And we also know B1 and B2. So the top 3 coefficients are fixed. We can determine these from N and D. Another thing we know is if we substitute x minus 1 into phi, we get a weakly type 2. And this is for these cases where n is odd in each case. So our factorization would give weakly type 2. Next, phi of x is totally real. All the zeros are real of this polynomial. It's slightly awkward to state. So I'll state it like this. In each of these cases, n minus d, x to x minus k, d plus 1 minus theta, phi. If we reduce this polynomial modulo 2 to the 7, then it should belong to this set N7, where this is something we defined yesterday. It's all of the possible characteristic polynomials of the side matrices modulo 2 to this one, 2 to the 7. So you might be thinking, where does the 7 come from? And the reason we use 7 here is because we can enumerate this set. So I think I'll just quickly remind you what this is. It's a point that I do want to clarify. Remember, this set is defined to be a set of all characteristic polynomials modulo 2 to the e such that S is an n-Seidel matrix. And so the point is, we can explicitly construct n7 for these values of n. So n 29, 41, 49. And if you make 7 bigger, or if you use 8 or 9, we can't necessarily do that. So the way we construct this is just we randomly generate Seidel matrices, compute their characteristic polynomial, reduce it modulo 2 to the e, and we keep doing that until we've built up enough elements that hits the upper bound that we saw yesterday. So that's where the upper bound really comes into play, since we know we found all of them once we hit the upper bound. All right, so now we've got some properties of phi. We're going to actually try to find them. So this is where I introduced the polynomial enumeration algorithm. So I'm not going to explicitly give the algorithm. I think I can define it intuitively using an example, but it relies on the following proposition, quite standard result, that if you have some totally real polynomial, so let P of X totally real, so all of the zeros are real, let this be totally real, don't need a hyphen, totally real, then the derivative is also totally real. And its derivative is also totally real. And so if you haven't seen this before, here's a picture of a polynomial. It's totally real. And I'll use yellow to draw the derivative. And so it'll come down like this and look something like that. And so derivative is totally real. Hopefully that picture convinces you. So I want to describe this polynomial enumeration algorithm, and we'll also use this in part 3 of the mini course. And so I'm going to describe it not by writing it down, since I don't think there's much return on investment for that. Instead, I'll just give an illustrative example. So this is an algorithm due originally to Robinson. Robinson's algorithm developed in the 1960s and further developed by McKee and Smith in the last few years. So it's an algorithm that's been sped up a bit over the years. And actually, we don't use the full power of what's been done. So we're not using too much more than the raw algorithm, which I'll try to describe. So in this example, I want to find all totally real, type 2 polynomials of the following form. So I know the top 3 coefficients. So let's say it's a degree 4 polynomial, x to the 4 minus 18x to the 3 plus 112x squared plus a3x plus a4. Okay, so I know the top 3 coefficients. This is the case for these phi. And I want to find all the possibilities for this. So this is pretty much what we're doing over here. So I just apply this proposition, and what I can do is take the derivative. So this is what I want to do. So I take the derivative, and I write that down. So that's just 4x to the 3 minus 54x squared plus 224x plus a3. So I know that this is also totally real. Now I can get some bounds for a sub 3. So let's draw a picture. Let's draw a picture of this graph without the constant term. So I'll just rewrite this polynomial, minus 54x squared. That's not what people normally do, is it? Let me do what people usually do. So I'll draw some axes, and I claim it looks something like this. And so this graph is of 4x cubed minus 54x squared plus 224x plus 0. Okay, so this I have a 0 term. And so I want to make this polynomial totally real just by giving some values for a sub 3. And so I can do that by working out these points here, where I have local minima and maxima. And if I do that in this case, then I get this point here is 294 point something. And this one down here is 263 point something. So the constant term just shifts this thing up or down. And so I need to shift this so this point should be below the line and this point should be above the line. And so I just read off these numbers. I see that I have 294 point something, 263 point something. And so if I want this to be totally real, it implies that a sub 3 has to be in this range, going from minus 294 all the way up to minus 263. 4. Okay, so to do this in general, you just need to work out these maxima. That will give you a range of values. And the next property we can use is it's type 2. So that will filter this down quite a lot. So since it's type 2, we know that 2 to the 3 has to divide a sub 3. And so we can just kill off most of these things. And so we find that a sub 3 is just one of 4 possible values: minus 2, 8, 0, minus 2, 7, 2, minus 2, 6, 4. And then we repeat this idea where we plug in each of these possibilities for A3. So it's kind of recursive. And so what we'll do in general is we'll form a tree. So at the top of the tree, we have our starting information. So I'm just going to write an array. So I give it the degree first, and then I give it the coefficients that we know. So we start off knowing that it's monic. So first coefficient is 1, then minus 18, then 1, 1. What was it, 2? That was our starting point. Then we worked out there's 4 possibilities for the next coefficient. So I'll write these vertically: 4, 1, minus 18, 1, 1, 2, minus 2, 8, 8. This one's 4, and so on. Minus 2, 8, 0. This one 4, the same stuff, down to minus 2, 7, 2. And the fourth one, it's like this: minus 2, 6, 4. And then you would just apply exactly the same idea again. And so this 2, 8, 8, you'll find the next coefficient. There's only one possibility. It has to be 2, 5, 6. This one has 2 possibilities for the next coefficient: 2, 4, 0, 2, 2, 4. This one just 1, 1, 9, 2, and 1, 4, 4. And so this gives us in total 5 possibilities for this polynomial. And this is how the algorithm works. And an important thing to notice here is that the degree is a serious problem if it's too big, because the degree is telling us how many steps we need to go down this tree. The width, the number of leaves coming out of each vertex, that's not such a big deal. And the type 2 condition really helps us there, because it really prunes off a whole bunch of different possibilities as you go down. So this is where the type 2 is giving us a lot of power by killing off a bunch of branches before it really gets started. But still, the degree is quite a big deal. So now I can give you the fruits of our labor. So this is the consequence of applying this algorithm, working out possibilities for phi. So I'll just summarize that again in a table. So D, again, we're just thinking of 14, 16, 17. N is 29, 41, 49. And here I'll just tell you the number of candidates I get for the characteristic polynomial. So the first one we get 31 candidates. Second one we get 22. And this one we get 194. And it might not be so satisfying just to see a number of candidates. So let me give you an example for each one. So example for degree 14 with 29 lines. This is a possible candidate characteristic polynomial. X plus 5 is the 15, x minus 3, x minus 4, x minus 5, and x minus 9 squared. This is multiplicity 10. This one, x plus 5, so 25, x minus 3, x minus 7 to the 6, x minus 8, x minus 9 to the 8, and this one, x plus 5 to the 32, x minus 9, 16, and x minus 16. Okay, so there's some examples of candidate characteristic polynomials that would correspond to potential systems of lines of this type. This brings me to the end of section 2. And now it remains to show that none of these candidates are possible. So this is the most fun part, part 3 of the course. And I'm very tempted to start, but I see I only have 5 minutes. But I will start because I really want to get through as much as I can of section 3, since it's the coolest part of the course. And so I'll just start off so I have less to cover. So now we've enumerated our candidates. Now we want to eliminate them one by one. And we want to eliminate them in the most systematic way possible. And so we have to develop some theory to do that, or at least recall some theory to do that. So this is the last part of my mini course about eliminating. Okay, and this stuff could potentially be more useful more generally, but I'm not sure. But we'll start off by assuming that M is some real symmetric matrix. So we're going to work a bit more generally. Matrix. And I'm going to give a bunch of definitions to start off. So let me define a few things. And I'll probably redefine these things tomorrow, but it's better to define things more than once. We've seen distance regular graph defined about 20 times. So the first thing I want to define, this is not very standard. Please let me know if you have better notation. Here I'm using capital lambda of n, and that's going to be just the eigenvalues of n, the set of eigenvalues without multiplicity. So eigenvalues without multiplicity, and I'll define the minimal polynomial of n to just be product, just to solidify this notation a bit, lambda in capital lambda n x minus lambda, and then a few more definitions. Next one I want is what I call the quotient. Again, please let me know if you know standard notation for this stuff. This is the characteristic polynomial of n divided by the minimal polynomial. Okay, I need to do another chalk refresh. And one more definition is my notation for principal submatrices. I use M square brackets I. This denotes the principal submatrix obtained by deleting the ith row and column, by deleting ith row / column. So the first theorem I'll just note for this course is one I assume everyone is familiar with, which is Cauchy's interlacing theorem. So this blackboard is now a whiteboard. But anyway, hopefully this is not such something you haven't seen before anyway. Interlacing tells us that if we have, so we let M be some real symmetric matrix with eigenvalues lambda 1 up to lambda n, then, and principal submatrix deleting some ith row and column has eigenvalues mu1 up to mu n minus 1, then lambda 1 is at most mu1 at most lambda 2 at most blah 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 lambda n minus 1 mu n minus 1 lambda n. Okay, so this is going to be quite useful for us. And a consequence of interlacing is the following nice property. Okay, before I do that, let me just define what I mean by interlaces. Again, this is all going to be pretty standard, but I want to get this stuff out of the way while I can. So what do I mean when I say interlaces? So definition, f is a polynomial, zeros, lambda 1 up to lambda n, and g is another polynomial with zeros mu1 up to mu n minus 1, then we say g of x interlaces f of x if we have this interlacing property that we just saw in the interlacing theorem, lambda n minus 1 mu n minus 1 lambda n. And so Koshi's interlacing theorem is telling us that the eigenvalues of any principal submatrix interlaces with the matrix itself. So a quick note based on this brings a bit of these notational devices together. So at this point, note that if some polynomial f, I'm using capital F, interlaces the characteristic polynomial of some real symmetric matrix, we can write f, capital F of x, as the quotient sub n, so the quotient of m multiplied by another polynomial f of x, where f of x interlaces minimal polynomial. Okay, that gets some theory out of the way before I show you the more exciting stuff that will happen from tomorrow onwards. Okay, so that's where I'll stop for today. Thanks a lot for your attention, and please ask questions if you have any.
Yes, questions for Gary.
Out of curiosity, what was the I presume this like example you have. I presume this example you had with the x to the fourth minus 18 x to the third actually does correspond to some actual like smaller dimensional
Example.
yeah, like sets of lines, or did you just construct that example and it worked?
Yeah, that's a good question. I came up with that. Actually, I made my PhD student gave me that example as when I was preparing for the Codex seminar. I think I also gave the same example. It's possible it comes from a Zyder matrix, but I can't remember off the top of my head. One extra remark I can give, I know it's not a question, but I wanted to say something about this one. This polynomial actually, if there exists a Zyder matrix having this polynomial, that implies the existence of strongly regular graph with 49 vertices. And this was shown already not to exist by Hammers. So some of the heavy lifting has already been done in some special cases. Just to give it a taste of the satisfaction of eliminating potential polynomials. Oh, yeah, question?
So maybe you explained this before, but
sorry. Yes. Do all the eigenvalues need to be real? Sorry, integers. Because all the examples that you here are integers.
Yeah, I know. I'm slightly biased. But the answer is no. The examples I gave are actually the most difficult ones for us to show non-existence of. So what we'll see next time is there's some phenomena where if you have some high degree factor, irreducible factor of the characteristic polynomial, it's somehow harder for the Zyder matrix to exist. But sometimes the standard techniques we'll see also kill off integer ones, but it just tends to be the ones having all integers, they're the most tenacious. They're the hardest ones to dispose of. So I think this one would have caused a big problem for us if it wasn't already shown to not exist. So we're kind of lucky this one's already been killed, because we have dreams of showing non-existence for strongly regular graphs using these techniques, but they just tend to be super hard to deal with.
But if they're not integer, then they have to be irrational, right?
Yeah. Right. Yeah, so algebraic integers, they come as group, and you can kind of, so you can kind of, make them fight each other, use them against each other, but integers are kind of on their own. They don't have any that's hard to make a crack in the wall for the integer case. Some very vague, unfounded intuition for them.
okay, so let's thank Gary again, and